Hey everybody, Evan again back with another video for NRTL model. And today, for part B, we will be using the NRTL activity coefficient that we found, which would be our gamma for last time, um, from part A1 and calculate the TXY and XY diagrams for our isopropyl water system at pressure at 101.325 pascals. And then from that, compare the location of the azeotrope of our model in our Python in the plots to find what we find on online. So just compare to see if they're similar or if they're not. They should be exactly the same, close to exactly the same. So we will be plotting that out in Python today. Now, before we start, I want to make some quick changes to what we did for our activity coefficient last time. I did realize that there was some mistakes and I put it out here. So if you remember, we had for our x's that we had none. And this is for our broadcasting. We had these all out for our X's. I deleted them this time because one, it does make it tricky because I practiced the code before, and it does make it kind of tricky and doesn't actually, it's too much for the code to process all the different type of broadcastings for the activity coefficient, and it just doesn't, it makes it stall out and not work. So I took them out for our X's. And also I forgot to add that our XG, which would be by up here, our XG, where's the equation? Our XG for our bottom, it actually does need to have a broadcasting as well, because if um if we pull this out, and I can actually show it real quick, pull this out. Let me change this to an X. Okay, shift enter. And then these all down. Okay, shift enter. So we pull out XG. We can see that it's a 1 by 2 matrices. And what we are trying to find is that our everything inside this right here is a 2 by 2. Okay. So we need to actually configure this so we can actually have to broadcast it so it can interloop multiple times to match what we're trying to divide by. So we do have to broadcast our XG for our left side of the equation. So that's what I forgot to add. Besides that, it does work. Ugh. All right. And now we can get started. Okay. So first, we kind of do what we did for if you remember our bubble point, dew point calculations, we would basically set up this something like that. Instead of having uh ideal conditions, we will have non-ideal conditions. That's why we use NRTL. So we'll first start with our bubble point, which we'll just do bubble, find our bubble point. But this would be we do of course our bubble pressure. And this would be respect our NRTL. So we're finding, and then this would be from our composition and then our temperature. Okay. Now from our bubble point, we need our our partial pressures, which is equal to our mole fractions times our activity coefficients, our gamma, and then times our vapor pressures. Okay, so that'd be P dot PVAP in respect to our temperatures in our function. Okay. And then we'll also be finding our total pressures. So we want to find our total pressures. That's the whole point. So if we know that the sum of our partial pressures will be equal to our total pressures. So we can just do P is equal to NP dot sum of our partial pressure. And then we have our pressure. So when we turn this, we want to find our total pressure. And then we want to also find our vapor molar fractions. Okay. So that would just be our partial pressure, not partial, yeah, partial pressure divided by our total pressure. All right. Shift enter. Oh, I put our column. Shift enter. Perfect. All right. Now let's go over to our bubble T. Now this is this is a little bit more difficult, especially for in our a non-ideal system. It's more just so for our temperature guess. If you remember, we have to have a temperature guess to find our actual temperature for this is for our bubble T. So it's kind of just a little bit more difficult, but it's not too bad. So we do bubble T in our TL system, and then again spectral fraction, and then this time be our pressure. And then our next thing we'll have is that we want to have a function for our temperature. So this would be just a zero. This is zero out to make it to zero out our function for our temperature. So you will just have this return our bubble T RTL. Oh no, our bubble P. Sorry, and RTL, and that'll be temperature. And here we'll be grabbing first our first value, and we'll be subtracting it by our actual pressure. So this is just telling us that it's doing the difference between what we're calculating pressures and then what we were given pressure. That's all it is. Okay. Then from there, now we start with our guess, our T guess. Before I get T guess, like I said, it'd be more complicated because you're not dealing with an non-ideal system, so two non-ideal liquids. So how do we do this? So one way we can actually do this is we were using Clapeyron, if you remember that. So we use our Clapeyron equation to help us find our temperature guess in this situation. Okay. So while we set this up, T guess equal to MP dot, which this just helps do the dot product again for two arrays. So our two arrays would be in this case our X composition, our molar composition for respect to our function, and then our Claudius-Clapeyron equation that we'll be putting into our NP dot. Okay. So that'd be X, more fractions, and then our Claudius-Clapeyron equation. So we'll have 1 divided by, and this is just to have our inverse, because when we have this, we'll figure out that to find our temperature, it'd be 1 over T at the end. So we have to flip it all over. So inverse the whole entire equation to find our temperature. So 1 over 1 divided by I. 1 divided by, and this would be the normal boiling points of our liquids. So TBN minus log of pressure divided by 101,325, which is our given pressure for this function, and this would be NP dot. Okay. Okay. And then this would be times. We have our gas constant divided by, this should be 1 here, divided by, what is it? I guess the hard part is just remembering the parentheses. Divided by NP dot diagonal. Diagonal. And then this would be inside the NP dot diagonal would be P dot HVAP. So our what is it? HVAP. What's HVAP again? Why am my mind's blanking? HVAP. I don't remember. HVAP. And then in here, I think we don't need actually this. Try to remember. HVAP. And then our normal boiling points again. TBN. TBN. Okay. Let me see what HVAP is because I totally forgot what that is. I'm having a brain fart. So that's not our specific vapor pressures. HVAP. Why cannot? HVAP. Heat vaporization. Yeah. Okay. Sorry. Heat vaporization for the liquids. I don't know why. I just forgot about that. Okay. Yeah. Yeah. Okay. Yes, our heated vaporizations, our HVAPs. And then so we have our T gas is our NP dot of our mole fraction, and then respect to our Clapeyron equation. Okay. So this will help define our bubble T. Okay. And then we'll put this into a root scalar. So we have a root scalar, and this will be have our function, so our F function. Then we have our guess. So our initial guess will be equal to our T guess that we just found. And the method we'll use is something called a secant. Okay. Second. Okay. Shift enter. And then we will put this into respect of res. Okay. And one thing we want to actually also put is that sometimes these scalars, these root scalars can actually non-converge. So we have to make sure we have to make sure that they do converge. So we can actually put an if not statement. And this is res converge. And this is just so us this is so we can just make sure that our secret our what's the word? Our root scalar converges. And then if not, it would let us know that it doesn't converge. So we're just not in the blue. So if not, fail, fail, and then for not res. Return, return, fail, and then for not res. Okay. So next part is now we just finished out the function. So we know that we're trying to find temperature. So temperature is equal to, and actually it'd be the same root scalar as we have up here for our res. But then at the end, we'll put a dot root to pull out the numeric function for the temperature. And then here we will have, just like we did for the top for our bubble P. So we have our partial pressures because we want to also print out our vapor concentration as well. So we do our partial pressures, which is X times gamma, X T times P pressure. And then we also have our pressure is equal to the sum of our pressure. And then we will just return RT and RPI divided by P, our vapor pressure. Vapor mole composition. Okay, so shift enter. Oh, keep forgetting to do that. Invalid syntax. All right, now we all good. All right. So then next part we need to do our dew points. Okay, and for our dew points, we're actually do something new. We'll actually use our an ideal case for our dew points. We could do NRTL, but for NRTL is actually much more complicated. And we want to, if we pick a bubble in RTL, you want to actually do the ideal case as well. So for we'll be using our ideal case for our dew point, which we actually did, if you remember, for our first video for our bubble point and dew point calculations. So what I would actually do, because I'm kind of lazy, is that if you want to remember what we did, we will pull back our dew points from our ideal case from our first video. We'll just copy and paste that up here. Okay, so that's our dew point P, and this is our bubble T. And it's the exact same. We're not changing nothing at all. So that's why I'll copy. If we had to change stuff, I'll definitely rewrite it. But it's the exact same thing as last time. So we can just pull both of these, shift enter, and now it's in our Python. And let me shift enter this, just make sure it's correct. Okay. So now we have our bubble points for an NRTL system and our dew points. So now the next thing we want to do is actually plot this out. So what we can start with, and actually, let's make sure this converges too. So let's try this out. And let me change this to Z for our compositions now. So let's make sure this converges. So bubble T and RTL, Z and P. Okay. Hmm. What the heck? Bubble NumPy has no attribute diagonal. Oh, it's talking about this. It must be. Let me see. Let me check the frames. T-guess, yes. So our T-guess, I think it's our P dot. Let me see. Props, it should be NP. NP should work here. NP dot diagonal should work here. It says my diagonal for NP is wrong. It should be right. I mean, it's spelled diagonal wrong, man. Unknown solver. Root scalar. Did I spell scalar wrong? Maybe. And it's for which one? For res. We have root scalar here. I don't know why it's not working up here. Maybe it should enter. Make sure. And I'm pretty sure it's the exact same thing. Root scalar. Yep. Unknown solver seconds. Oh, it's the. Let me make sure. Roots. I may have spelled that wrong. Scalar. Python. Let me see the different methods. Yeah, there is none like this. Yep. One. There you go. Second. Okay. Pi. And pi gamma. What's wrong with our pi? Pi is equal to gamma times p dot p vap of t. Hmm. Problem was back with the res scalar. What's the problem here? TS method. Second scalar. This should be correct. What is the problem? I'll be right back, guys. Let me check what the problem is, and then I'll be right back. Okay, guys, so I figured out what the problem was. I forgot to put in the defining functions for gamma. So I need to put that in. And now it should now you see that the bubble tea now converges, there's no problems, and now we are good. Okay, so now let's plot this out. Okay. So what we will do is that we will start with our x1s, and our x1s actually be equal to NP length space. And we can just do from 0 to 1, represent our mole fraction, and then we can just do like 150 points. All right. All right, next we'll do our temperature, so TS's, and then we can equal this out to that, and because that will be depending on our x1 values, and we already have a temperature, have a calculator here for our temperatures. It's got to be just represented for our x1 values. And we do the same for our y1s. So let me put this down. Y1s be dependent. Okay, so next we'll put for x, what is it? Okay, good. So guys, I forgot the problem. So it was just that I forgot to put in my defining functions for our gamma up here for our bubble P. So now from this this now converges and now everything works. Okay. So now let's plot this out. Okay, so we will start with our x1s. And our x1 values would just be a range of values from 0 to 1. And we would just say we will need 150 points. Okay. Next we'll put our TS, our T's, our temperatures, temperature data points, and our Y data points, Y1 data points. And this is be bracketed off to indicate that this is dependent on our X1 values. Because remember, again, we just calculated what our temperatures and our vapor composition should be. We just have to be dependent on what our liquid composition would be. Okay. Ones. Okay. So now we'll do for X1s and X1 and X1s. We would do temperature and then our Y1 and Y2s equal to our bubble T and our TL, and then P dot array of our X1 and then 1 minus X1. Yeah. All right, and then this should be respect to next will be pressure. Okay. And then what we want to do now is append these. Oh no. We want to append these, so we want to append our temperature. So our TS's dot append the temperature. And then our Y1s needs to be appended as well. So they are frequently updated to new points with our Y1s. Okay. Okay, so we should there. Would be what's wrong? Saying an array with element. What's wrong? Let's see. Oh, and then this should also be it. S Y1. Oh, that's why wasn't defined. Y1. There we go. Good. Perfect. All right. So now let's get to the plotting part. Okay. So now what we will do is that we actually want to interpolate our data points so um they can be more better for plotting purposes, basically fit the line better than what we're trying to find. So we actually use our Akimi 1D interpolator that we did for our bubble dew point calculation. So what we want to do is we'll do for our start with our Y interpolator. And this will be equal to Akima 1D interpolator. And this should be our X1s, should be for our first our X, and then our Y1s. And then we'll do the same thing for our X interpolator. Our X interpolator. Or to be equal to Akima. Make sure we can just copy and paste this as well. So copy and paste. And this time this would be Y1s and X. Okay. Should enter. Oh, I keep putting L. I was like, why is it keep doing that? I keep putting L instead of 1. Okay. So now let's make our subplots. So fig equal to make subplots. And we want 2 graphs here, side by side. So what we'll do is do rows is equal to 1. Then our columns will be equal to 2. Okay. And then like we said in our prompt, we are trying to find TXY and XY plots. So This one would be our TXY, and for this we do fig, uh, the add scatter, and our Y's, and your X would be X1s, Y's will equal to our TS, mode, the lines. And then for our rows, this be our first graph. So rows equal to 1, columns equal to 1. And then we can actually copy and paste this. And then the difference would be is that our X now is be our Y's. Okay. This is our TXY. And now for our XY, we can actually copy and paste this again. But instead of our Y being TS for temperatures, it'll be for our vapor composition. So Y1s. All right, and our column B2. And then for our last part, actually, we wanted to say regular XY diagonal line to run across the graph to see our difference. So we would just do a 0 to 1 for both our X and our Y. So, and this also be to column 2, and this hopefully works out. Let's see. Bada bing, bada boom, it works. So we have fig dot update just to make sure it looks better. We do width, let's just keep 600. Height of 500. Actually, we do 700, make it wider. 700, and then polydark, template, and this should be polydark. All right, sure then. What did I do? What did I do? What did I do? With height, template, polydark. Huh? What's the problem? I think it's plotly one. I did. I was like, what? Plotly. There we go. All right. So here is our graph. And if you want to look at something online, I pulled this from Wikipedia. But the left side represents our, actually, let me make it a little bit longer because it's kind of compacted. Okay, perfect. So this is what we have right here. This is our TXY graph, so our temperature represent temperature versus our composition graph, and this is our composition graph based on our represented off versus a just regular diagonal line. And as you see, the left side is what we see from our online. This is what I got pulled from Wikipedia. But I see the gaps in between is when we see our HEOtropes, and then middle interceptions, and when we see separation in between the two lines. And yeah, as you see, this what we get pulled from online actually does match what we have for our mold composition, which is perfect. That means we modeled our NRTL model very, very well. So that's very good for us. Yeah, so yeah, guys, this is our model for NRTL. Hopefully this helped you guys and worked out. So perfect. And I'll see you guys in the next video when we do our part C and part D. All right. Bye guys.